And then we started also the subtraction. Then we did one also this thing, comparison. Compare. Now the compare instruction is in arithmetic, but it uses, because what we do in compare, we check whether they are equal, not equal, greater than, less than. Okay? So we use, in order to compare, we subtract the two values and see if the answer is 0, both are equal. Answer is positive, the first one is bigger than the other. If the answer is negative, the second one is bigger. Okay? So this is how we decided. Now, so in this one, we were comparing one value with the other one. Now, there are other instructions which are string related. That means, but they also use compare. So in this compare, we were saying one value being compared with the other one. Now there is another instruction which takes this value to compare it with the whole array, which equivalently means we are searching for the value. So we compare first this one with the first value, equal, we got the value in the array. If not, go to the second value, compare. Not, go to the third value. So this means we are actually looking for this value in this whole array. This is called compare string scan. So we scan the string as a byte, as a word, as a double word. And another one is the compare string now. So that means we have two strings. We want to check whether first one is equal to the first one, second one is equal to the second one, third one equal to the second one. So we are comparing the two strings. So these are the only two, but these comparisons use again subtraction. Do you remember what we discussed in the string? What were the three conditions? Whenever we think of a string, number one, what is the size of the string?
Address.
Okay? What are the addresses of these strings? Because the strings are stored in the memory.
Increase.
What is the address in the memory? Number three, when we are continuing with the string, is the address increasing or decreasing? These three things. So let's see in each both. You will. So in scan string, we can have a byte scanning. We can have word scanning. We can also have a double word scanning. Okay? You see here now, let's say we are searching for a value. What is the value? 20. Move 20 to A. Okay? We are looking for value 20 in the string which is in the memory. You see here CLD, we can also have STD. CLD means direction flag is 0, which means addresses will be increasing. What is the size of the string? 256 goes to CX. So we told addresses will be increasing. Size of the string is 256. And then where in the memory is the string? Move to DI, offset the address, right? The block is a variable which is equivalent to some address. We have not defined what is a block, but you consider any value, right? So some value as an address is in DI. So we defined the address in the memory, which is the beginning of the string. CLD is after the first one, the addresses are increasing. Total size of the string is 256. Which value we are looking for? 20, and we are doing it as a byte. You see here, repeat while equal string byte. So you are looking for value 20 in a string of size 256 stored in the memory. The beginning of the address is in the DI. See? So what this scan string will do? Compare, which means it will use subtraction. And subtraction means, remember, in this case, subtraction means we are not interested in the answer. We are only interested if the answer is 0, not 0, positive, negative, right? The other one, which is compare, so this one was scan string, and now we are talking about compare string. That means we are checking whether these two arrays are same or not same. So this is compare string, byte by byte, word by word, double word by double word. Okay, you see here now, again, CLD or STD, size of the string defined in CX, okay, since it's a byte, let's say 10, since we are talking about two strings, the offset address, one is in SI, another offset address is in DI. So we have two strings, size of each string is 10, and each time after comparison the address will be increasing. And now you see here, repeat while equal to compare string byte. Again, this will be just subtracting one value from the other. Okay? If it is equal, continue it. If it is not equal, skip it, because purpose was whether we are comparing. If the first two, anytime they are not equal, we ignore it. That means now our job is done, they are not equal. For equal, we have to do complete, right? Until all elements are the same. If one of them, they are not the same, we abort, right? We leave the loop. Okay, so once this is done now, we move on to the, after add and subtract, now multiplication, and this is the instruction, mul. And the purpose of this mul is multiplication. Remember, we had for addition few of them, right? Add with carry, right? Add, exchange, add, increment, like that. Here we have for mul, I mul, am, pre. Then division, div, I div, aad, and then the other two. Now, there is one thing, add and subtract are very simple. Why they are simple? For microprocessor, because if I'm adding byte with a byte, answer is always a byte. Maybe I will have a carry, right? If I subtract, I have one 8-bit or 16-bit, another one will be 16-bit. I subtract, I might have a borrow, right? Again, the answer will be 16-bit. But in multiplication, we have to be careful. When we multiply, maybe our answer will be big. If I multiply byte by byte, maybe answer is bigger than a byte. Okay? Like byte is equal to 200, right? 200 is a byte, because less than 256 is a byte. Now if I multiply 200 by 210, it becomes bigger than a byte. The answer is very big. Okay? So this is the first thing in mul. Note it down. Whenever we will multiply the two values, answer will be the double size. This is what they decided in the design. That means we will go with the double one. If the numbers are similar, it's okay. We can place a byte in a word. But the answer will always be allocated as a double size. But the numbers have to be the same. You cannot multiply. This is another thing. You cannot multiply. Although I can multiply 3 by 500, right? But how the microprocessor will do it? According to the rule, you have to make them same size. Like we were doing in here. Add and subtract. You cannot add AL with BX, right? Okay? So same thing here. You have to make them equal size. And then when you multiply, answer will be the double size. This is the mul. So this is what you see here. If you And another thing, the first operand is always in the accumulator. Always. So if you multiply 3 by 6, place one of them into AL. Because both are byte, place them into any one into the accumulator. And it will be known. We will place one of them into AL, but when we will say mul, then we will only say the other operand. Let's say I have one value in AL, another value in BL, so I will simply say mul BL because the other value is already understood by the microprocessor, it is in AL. So that's what you see here, mul CL. This means the other one is in AL, right? So that's why you see AL by CL, and answer will be the double. So that's why instead of AL now you get AX. This is the rule for the multiplication. The one of the operand is always in the accumulator, and the answer is the double size. Same here, mul BX, which means the other value is in AX. Since this is 16-bit, the other will be also 16-bit. Now I'm multiplying 16-bit by 16-bit. Answer by rule is double, 32-bit, right? If it is real mode, I will use 2 registers. Because in the real mode, register is 16-bit. Are you getting the point now? If I'm working in protected mode and my values are 16-bit, then the answer will be in EAX. Because I have the access to the 32-bit register. Calculator can do the multiplication for you, okay, but positive. So if you have it, you can verify, multiply 2 by 8, you can get the answer. Just in calculator hex mode, mul 2 by 8, you will get 10. Similarly, you have 102 multiplied by 1001 and you will get the answer. Multiply 2 by 8 in hex mode. You know how to do it?
No.
You don't know? Hex mode? There is a hex mode. Anyone who did it? You got it? Is the answer correct? 10 hexadecimal. Tell her, how did you do it? Then hex mode. Now 2 multiplied by 8. Do you get 10? Okay? Alright. So we can multiply a register with memory, memory with register, register with register, right? But remember the rule. The rules which I told you. One of the values has to be in the accumulator. And the size answer will be always the double. Another example of mul. How will I do 320 with 42? Please. Let's see the example. What is the target? 320. What will I do? Move one of them into the accumulator. Which register shall I pick? Byte or 16-bit? Why? 42 is a byte, but 320 is a word. So the rule says both have to be the same size. So pick any one, put it in AX, the other one in any other register, right? So let's say I say move 320 to AX or BX, doesn't matter. And then I say move to BX 42. Then I say here mul BX. Job done. Where will be the answer? Answer will be now, instead of 16, 16, now it will be 32. How will I write ax dx? This is where I have the answer. Okay, so you see here. Okay. Now another question comes here. The numbers are negative. So far what we did in the previous slide, which was here, and the experiment you did 2 by 8, right? You can also do 102 multiplied by 1001. Okay? These were all positive values. Now if the numbers are negative, microprocessor always converts the negative numbers into 2's complement. So if I have one is -1, another one is -2, then if I multiply, so if E is 2's complement of -2, 2, and FF is 2's complement of 1. If I say multi-L's, answer get FD02. Is this the correct answer? What I'm expecting? I'm multiplying 1 by 2. I'm expecting answer 2, right?
Yes.
Because I'm multiplying 1 with 2, right? -1 multiplied by -2.
Yeah.
I'm expecting 2. But what I'm getting? FD02. This is wrong. This is not the one which we want. Calculation is correct. So what is the point here? Point here is mul can only be used for positive numbers. Microprocessor doesn't know the numbers we are putting in AL and CL, they are positive or negative. Doesn't know, right? So we have to tell the microprocessor that these numbers are negative numbers. So that's why after mul for negative there is IMUL. So now the microprocessor will understand the numbers they are multiplying, they are the negative values. So do not use mul for so here you see, I have it here, now I say IMUL, I will get the correct answer. Okay, what happens because we started from the beginning, real mode, protected mode, flat mode, right? 16-bit processors, 32-bit processors are 64-bit. The rules I told you before, they are the same. Now if it is 32, you see here, bigger value 32 goes in EX, another value bigger than word goes into EPX, and I say here mul EPX. So the procedure of multiplication in the microprocessor, whether it is a real or protected mode, the same thing. Since we are multiplying 32, answer will be 64 bit, the double size. Okay? Same thing happens with the 64-bit microprocessor. You see here, instead of E, the registers are R, right? RAX, RBX, so I can always move one of the values in the registers RAX, RBX and mul RBX like that. So the rule for multiplication, whether it is positive or negative, is same in real mode, protected mode and the fluid mode. Okay, now if the numbers are BCDs, because so far what we did in mul and IMUL, the numbers were hexadecimal, right? Do you remember what we did for BCDs in the aid and subtract? Anyone remembers? What were the extra instructions? Remember in the last lecture, let me repeat. Quiz 2 is coming next week or not?
Yes.
Okay. Because it's complete silent. We just finished add and subtract in the last lecture. We said if the numbers are hexadecimal, right, we are binary, we will use add and subtract. But if the numbers are ASCII, after add, we say, correct?
Yes.
And if we have a BCD values, then, correct?
Yes.
Same thing is in multiply now. If the numbers are BCD is what we will do. We have, it just X for multiply. Okay, telling the microprocessor, because microprocessor doesn't know the number 3 you write, is it hexadecimal or BCD, because number 3 is same in both number systems, right? So from 1 to 9, 0 to 9, the numbers are same. So that's why we also always have to tell AAM. So this is what you see here. After mul-BL, we have AM. Okay, go in the hex mode. Go in the hex mode. If you multiply 9 by 9, what will you get? Again in the calculator, whoever has it. 51, which is correct. So is it 9 by 9, which I'm expecting 81, right? 9 multiplied 9 is 81. But the microprocessor is giving you 51. So this means microprocessor does not know the numbers are the decimals. It is treating these 9 and 9 as a hex. Okay? So that's why after mul-BL, we have to do AAM, which means treat these numbers as a decimals. And you will find 9 by 9 as an 81, but these are unpacked. How do you write 81 and unpacked? 08 and 01. 8 as a byte, 01 as a byte, because the BCDs are unpacked. So now, let's do the final. What are the summaries of the mul? Number 1, multiplication operates on same size numbers, right? Either both are byte, both are word, both are double word, or even 64-bit. If not equal, place them into equal, because mul and imul works on the equal size values. Number 2, the second operand is always in accumulator. Put, that means place one of the values in the accumulator. Number 3, for negative numbers use imul, for positive mul. And the other one, which is not written here, the answer is always the double size. Fourth one, for unpacked BCDs use AM after mul or imul. Okay, let's go to the division now. Do you remember the rule? Do you remember the rule for multiplication which we just did? From the beginning, we said whenever we multiply the two numbers, it is possible that the answer will be the double size, right? But in division, it is opposite. When we divide, most of the times the answers will be smaller than the original values. Okay? Number 2, in division we have two answers, quotient and remainder. Okay? Others are same like multiplication, like one of the values has to be in the accumulator, correct? And for mul, if the numbers are negative, we said imul. Similarly, for negative numbers here, instead of div, we will have idiv. But 2 points are very distinct. Answer is not bigger than the original size. It can be same or even smaller, right? But the answers will be, there will be two answers, right? One is the quotient, other one is the remainder. Okay? Third one, since we need two answers, okay, and we expect that the quotient, which is the answer, divided answer, will be smaller, so we want that the numerator has to be the double size than the denominator. Double size, so that when we get the answer, half of it for the quotient, when we get the answer, and the other one is the remainder. So here, when I say div BL, this means this is the second operand. First operand will be in the accumulator, but the double size, because the numerator we said has to be the double size. Okay? Div BL means AX divided by BL. The numerator, the other coefficient, other operand is of double size. Is of double size and in the numerator. If it says div CX, that means the numerator will be 32-bit because this is already 16-bit. Numerator will be the double one. And we will have two answers. If it is a dividing by byte, quotient in AL, remainder in AH. The same one, we will have it here. Okay? Not necessarily in this order, maybe I think quotient is here, remainder is here. But we will see in the example. Okay. Let's say we have this one. Okay? You can check in the calculator. AX is already given 0200 and BL is given, you see here, one is double size than the other. This is byte and this is word, right? Already given. So we will say here div BL, which means AX divided by BL. You have the calculator and you can check the answer. 200 divided by 4 in hex mode. 80, right? And 80 is the quotient. If you don't find the other one, this means the remainder is 0. So the answer is in here. AL, AH. This is quotient, this is remainder. So if you are finding 80, this means these values are 0. There is no remainder. So whenever, remember like in mul, I told you, if the two values which you have, they are of different size, make them the equal size, right? But in division, if you have both same size, make sure your numerator is the double size. Because in division, we want the numerator to be the double size. We will do the example. Again, for negative numbers, use div, idiv, right? What do we do here? I want to divide minus 2 by minus 2 by 2. What do I do? What will I do if I have to divide minus 2 by 2?
Minus 1.
This is a negative number, right? So first thing is you have to write this one into 2's complement. What is minus 2?
0.
Minus 2 in hexadecimal. 2 is 1 0, right? 1 1 0 1 and 8 1. This becomes 1 1 0, right? So which this one is? This is E, right? 1 0 is E.
Yes.
And we have to make, again, 4-bit is nothing because this is just 4-bit, right? Normally our minimum is a byte. So we write here byte now. So this will be, this is FE. I can show it to you. Nobody, I thought you can do it. Here you see, multiply -1 by -2. -1 is FF, -2 is FE. Now you see -2 is FE because we consider a byte. Okay, so question is FE divided by 2. Okay, so now this is what we have to implement, right? But now division says the numerator has to be the double size. Okay, so this is, see here what we do. The div will not work, we will do idiv, right? Example of, this came another one, maybe we will come back to it later. So now, how do I make, this is a byte, right? My concern is if this is byte, div requires or idiv requires this has to be the double one. How will I make it double one? There is an instruction to make it. Normally, what we do if I have a 8, like this one, I had 2, right? I have, let's say, 3, 2, I make it double size, I wrote this word, right? 0032. It's a 16-bit, right? But now, if this was negative, by placing zeros, the value became positive. So placing 0 is not right. There is another instruction which always takes care of this sign. If it is positive, extend it as a positive. If it is negative, extend it as a negative. So instruction is convert byte to word, CBW. So the purpose of CBW is from byte, make it double. So CBW, which means convert byte to word. Another instruction is convert word to double word. How they make it? What is the value here? Over there we are considering FE, right? So FE, F, this is F, E, okay? How I will make it a word? From byte to word, this instruction. What it does, please pay attention here because the operation of these two is the same. Principle is, it always looks what is the MSB. If it is 1, repeat once.
Okay.
If it is 0,
Repeat 0.
repeat 0.
Okay.
So what is after FE? This is FE, right? So now this will be
SF.
FFE. You don't have to do it, just take the microprocessor CBW. So what I will do here, since I want to divide this one, come back here, move FE, this is the numerator, right? To AN, always the numerator is the accumulator in the division, okay? Then I say here convert byte to word. So now value is in AX, which will be FFFE. In AL I have FE. Now this means AX is equal to, now this is the one. Correct? What is the other value? 2. Move. Let's say I do here BL 2. So I have 2 values now in 2 registers. What should I do? Question is divide, right? How will I divide now? I div because I know the number is negative. One of them one is negative, right? I will say here I div BL, which will be AX divided by BL. Any questions here now? So this is how we implemented like this. So this is called sign extend. That means taking care of the sign and extend it, right? Byte word, or if it is a 16-bit, I want to make it double word, then CWD. Okay. Divide 4F by 2C. How we will do it? 4F goes to AL. I have to make it double size. Convert byte word and then move 2C to BL. Div BL because both are positive. I use div. Here one of them was negative. I use idiv. Is it clear now? Okay. Maybe we will have another example. -2 by -1. What will I do? This is easy like we did it here, right? Exactly the same way. What do I do now? Both are negative. Write them into hexadecimal. -2 is FE and -1 is FF, which we did before also. You can convert into 2's complement also. So, convert into 2's complement. FE is -2, right? We put it in AL. Convert byte, and another one, -1 into BL. The first one we say, convert byte to word. Okay? Now, since the values are negative, I did BL. Okay. So what now? What are the issues? Summary. Number 1. In division, right? Number 1. The numerator has to be the double size. If not, make numerator the double size. Okay? Another one. The numerator is always in accumulator. For negative numbers, use idiv. What was the rule for BCDs? For multiplication, AAM, right? And here for div, it is AAD. Adjust AX for division. Okay. Now here is another thing. This code is taken from the book, but we need to understand. Now, this is only in division. Remember we said there are 2 answers in the division, right? 2 answers. One is the quotient, other one is remainder. You just place it, it's okay. But our practice is something else. We always try to round, right? If it is 3.05, 3.2 equivalent to 3. If it is 3.7 equivalent to 4, right? So how do we do that? Can we do this thing also in the microprocessor? Can we tell the microprocessor round it? How it will round it? What is the rule we do? What is our rule? We always compare the octadecimal with 0.5, right? This is our practice generally. So this means we want to compare this value equal to 1, right? 0.5. So if it is the remainder, what we get, the quotient after decimal, if it is greater than 0.5, we add 1 to the quotient, right? If it is less, we make it 0, right? So this is what we did here. Sometimes in our programming, we round. If it is not required, don't do it. You will have both answers anyway, quotient and remainder. But if you have to, then you have to read the remainder, compare it with the 0.5. Okay? So this is what you see. After division, let's say we did the division, we have div BL means what? AX over BL, right? Which means my AL is the quotient and AH is the remainder. This is my remainder. This is my remainder, right? So when I'm saying in the first line div BL, this means I am doing AX divided by BL. And my answer will be in AX, lower byte is the quotient, higher byte is the remainder. Now our focus is here. Okay? And we said we always compare to the half, right? So how can I do half? Instead of saying half, I double it. Double the remainder. Add AH and 2H. So I said here, this one is multiplied by 2. Okay? So instead of comparing with half, we said compare to 0.5, right? Instead of that one, I said double it and compare with 1. Same thing, right? So this is what you see here. Double it and then compare whatever the double value is, the actual value. If it is below, forget it. If it is not below, increment the quotient. This is what you see here. I am dividing it, doubling the remainder, comparing with the BL. If it is below, forget it. If it is not below, increment the quotient. So this means this can be done in the divisions. If it doesn't ask you to do rounding, leave the quotient and remainder. You have the answer. Okay, just read the register, AL and AH separately, you have the values. But if you are supposed to do rounding, then you can round it. What happened here? Okay, so we can, if division is unsigned, okay, so rounding here. Now what, like multiplication, remember the multiplication? What we said, in the real mode or protected mode or the flat mode, multiplication operation is the same in the microprocessor. Same thing is for the division, whether it is a real mode, whether it is protected mode, whether it is the flat mode. Okay? From 16-bit to 64-bit. We can always have a same 32-bit division or 64-bit division. The idea remains the same. Use of register remains the same. Div and iDiv, mul and imul. Whether they are 16-bit, 32-bit or 64-bit. Same thing. Okay, now let's see if we can do this one. This is a somehow modified exercise from the textbook. Let's write a code for this one. If you can understand it, this becomes easy. We just did everything. This is a good exercise for the whole lecture today. What are we going to do? We said we multiply 12 by 258. Okay? This is the requirement. And then divide the answer by 2985. This is what we have to implement. Numbers are positive, right? So
فلسطين شو بدهم في أول
12 by 258. Now what do I do if I want to multiply? Number one, both values in multiplication have to be in the same
Same
size
size.
registers, right? Which register will I use? AX and BX. Okay. So move. Which one you want to put in AX? 2, 4, doesn't matter, right? Okay, move to BX 12. Okay? Now what will I say? Mul which means AX multiplied by BX, both are 16-bit, and the answer is 32-bit, which is AX dx. Don't write EAX because our operation so far is the real mode.
Okay.
If we already says that we have access to the protected mode, then you can use
Okay.
EAX as an answer, which is 32-bit register. Now we have this one. Now what we have to do?
2985
Where will you place this one? Are these numbers? Which one? Here the solution is not given, right? Yeah, here, right? Multiply 12 by 258. Okay, now here comes the thinking, what shall we do with it? Move to 2985 to pick any other register. Which one?
CX.
CX. Why not others? Because
You have.
our answer is already in AX dx. We cannot override these registers, right? Now what do we do after that? So now what do we do?
For
Div? Div what?
لا بي
What is the division rule? This has to be the double size, right?
Yeah.
Which we already have. This is the answer. And we are dividing by CX. So what will I say here? DF CX, which means it is expecting the other one, the double size, right? So which means DX AX over CX. Now tell me where will be your quotient in the answer? Who said AX? Correct, right? So in AX, so whatever is the numerator, answer goes in the numerator. In AX, I will have a quotient. In DX, I will have remainder, depending whatever is the answer. If I just change this one, multiply minus 2, minus 12 by 258, what will you do?
We add
Are you getting the question what I am saying? I said multiply minus 12 by 258. Everything remains the same. What will you do? Do not put positive value here, right? First write 12 as a 2's complement. Okay? 12 in a byte. So what will be 12? What is 12? 12 is decimal.
1100. Hexa. I just said that one.
If let's say this is a hex, right? So this will be
Sorry.
right. So this will be
FF.
0110, right? FF EE.
EE.
Okay. So we will say here move 12 to BL, and here what we will say? Do you remember? Don't do like this one. This was just our practice. But in the programming, what you will do, move 12 to byte, and then you say convert byte to, everything else remains the same. 12.
It will be
Not 12, sorry. 12, not 12. What was this one? EE. Correct? This was our EE. EE to BL, and then convert by 12. Because the value is minus 12. Everything else remains the same. What will be this one? See if we can solve this thing. Again, this one is not solved for you. What is the question? Yes.
We change bx to bn. Then we say multiply bx or bn.
No, because once we said byte to word, so now it became the word which is bx. Okay? Now here, what is the first one? Move A1 to AL. So this is AL, and we are placing A. How is A? 1010, and then 10001. This is the answer of the first one, right? Move AL to move A1 to AL. What is the next one? Convert byte to word. So from byte, another byte, right? And what is the rule for it? Look for MSB, right? Repeat it. 1 1 1 1 1 1 1 1. This became the second instruction. Based on this one, right? MSB. What is the third instruction? Convert word, which is this one. So this means, remember, always look at the boundary. What is the boundary of a byte? 1. What is the boundary of a word?
1.
This one, right?
Yes.
So then again, another word, because I have to make it double word, right? 1 1 1 1. So what will be the answer? F, 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 F. This is this one, and then F, F, A,
1.
1. This is the answer. This is in AX. This is in
dx.
CX. So my question, for example, could have be, what will be the final value in dx? Okay? So you just go and reach it, and dx will contain 4f's. Okay? We stop here. That's also the end of, is there another one? Okay, so we finished. Why we want to stop here?